Welcome back to series on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we're going to do two examples of the alternating series test. Now, if you need more explanation on the mechanics of the alternating series test or simply recognizing whether something is alternating series, please go back and visit the first alternating series test video. All right, let's dive straight into the example. So we've got a series from n equals 1 to infinity of -1 to the n plus 1 over n. Now, you might be able to recognize this as alternating straight off the bat. If you need to, you can write out the first few terms, which I've done. So if you plug in n equals 1, and then 2, and then 3, and so on and so forth, we see that we get 1 over 1, and then -1 over 2, positive 1 over 3, -1 over 4, and since the signs alternate, this is in fact an alternating series. Now, the two criteria require us to know b sub n. So what is our b sub n for this alternating series? Well, we basically just take the argument of the series and remove the alternating part. The alternating part is just the -1 to the n plus 1. So if we remove that, all we're left with is 1 over n. That's our b sub n. And so the alternating series test says we have to pass these two things. The limit as n goes to infinity of b sub n has to be 0. Well, let's first worry about that. So if we take the limit as n goes to infinity of our b sub n, which is 1 over n, does that equal 0? Well, yes, it does. If you were to essentially plug in infinity into the denominator here, 1 over infinity is in fact 0. So we pass that first criterion. Our second criterion says that the 1 over n, or our b sub n, must be decreasing. We can put it this way: b sub n has to be greater than b sub n plus 1. So our b sub n is just 1 over n. And if we look at our b sub n plus 1, that's basically everywhere we see an n, we just put a plus 1. So our b sub n plus 1 is 1 over n plus 1. And this would have to be true. 1 over n would have to be greater than 1 over n plus 1. And in fact it is. If we imagine taking some of the numbers from this series, let's start with 1. That's the first number included. 1 over 1 is greater than 1 over 1 plus 1. That's saying 1 is greater than a half. If we plug in the next term, 2, 1/2 is greater than 1/3. So actually for every single number, for all n that are included in this series, or for n greater than or equal to 1, this is true. This relationship is true. So because both of these criteria are satisfied for this alternating series, this series automatically converges. Okay? Now, this is half of the problem. In the other half of the problem, we need to determine whether or not the convergence is conditional or absolute, and I go over that in the previous video. So if you get a situation where both of these are satisfied, you know it converges. What you don't know is whether or not the convergence is conditional or absolute. Now, in order to determine conditional or absolute convergence, all we do is we take the absolute value of the original series. So now we have the series from n equals 1 to infinity of the absolute value of -1 to the n plus 1 over n. Now, generally what happens is the alternating term goes away, and so when we do this, we're left with the series from n equals 1 to infinity of 1 over n. Now, this happens to be our b sub n, and that happens sometimes. Okay, so we need now to determine whether or not this series converges or diverges. Well, this one's a really easy one. This is the harmonic series. Remember, the series from n equals 1 to infinity of 1 over n, this is the harmonic series, which we already know diverges. And so now what we can say is because the absolute value of the original series diverges, because it's the harmonic series, when this diverges, that corresponds to conditional convergence. Okay? Now, if this series, in another example, we'll see one where this happens, but if this series converged, then that would correlate with absolute convergence. But because it diverged, it's conditional. So diverge goes with conditional, converge goes with absolute. All right? So now what we can say is the original series, which I have right here, and also in the previous slide, this original series not only converges, it's conditionally convergent. Okay? So again, just to regroup what we did, and we'll do this in the second example. Once you know it's alternating, you conduct these two little tests right here. Okay, this is the alternating series test. If both of these criteria are satisfied, it converges. But then you need to determine whether or not it's conditional or absolute. So you then take the absolute value of the series and run any of the tests from that we talked about in the series chapter. Okay, and because the absolute value diverged, the convergence is conditional. Okay, and that's kind of the steps we're going to go through for all of these, except for ones like this. And in this case, I'll go ahead and prelude to this. We're actually going to fail one of these criteria. So let's see what happens there. Here's our second example. We have a series from n equals 1 to infinity, and it's negative 1 to the n times n squared divided by the quantity n squared plus 5. All right, so the alternating series test requires us to know b sub n. So what's our b sub n? It's basically everything minus the alternating term. So we remove the negative 1 plus n, and our b sub n is therefore n squared over n squared plus 5. All right, now we know our b sub n. Let's go ahead and take the limit as n goes to infinity of that b sub n and see if it equals 0. Well, here it is. Limit as n goes to infinity of n squared over n squared plus 5. Well, this limit is technically an indeterminate form because if you plugged in infinity, you'd have infinity over infinity. So you can use whatever kind of limit solving technique you want. I'd probably just say L'Hopital's rule, or just recognizing that these are the same power of n, so it's just the coefficient of that divided by the coefficient of this. And any way you look at it, this limit is 1. All right? Now, 1 obviously does not equal 0. Therefore, this first criterion fails. Now, if the first one fails, you don't even have to look at the second one, because in order to pass this first step in the alternating series, it has to pass both of these criteria. Okay? So unlike the first example where we passed both of them, now we failed one of them. And it could be both of them, or it could just be one of them. One of them's good enough. So it failed the first one. We're not even going to check the second one. We're just going to default to it fails either of them. But that does not necessarily mean that the alternating series diverges. What the alternating series test tells you, at least this first part of it, is either it converges or, in this case, it's inconclusive. Okay? So what we have to do if it's inconclusive is we just have to run another test. So a good rule of thumb is if you get a situation where it fails either one of these and you determine it's inconclusive and have to run another test, the test for divergence is normally a pretty good bet. So let's do the test for divergence. This says that you take the limit as n goes to infinity and basically see what it equals. Okay? So the limit as n goes to infinity, negative 1 to the n power of n squared over n squared plus 5. So we have to take the whole argument of the series with the alternating term. Now, remember, this argument could be broken up as a product. We could have negative 1 to the n power times n squared over n squared plus 5. Limit as n goes to infinity. I didn't change the value of this limit. Now, you're not technically supposed to do this, although it actually works out in this case, and really in any case like this. We already know that this limit, if we just take the n squared over n squared plus 5, we know this limit is 1. So this right half over here after the product sign, this is 1. And so we're essentially taking the limit as n goes to infinity of negative 1 to the n power. Now let's think about that for a minute. That's an alternating term. So essentially what's going to happen as you get bigger and bigger and bigger, you would either have negative 1 or 1, negative 1 or 1, negative 1 or 1. In other words, this limit never actually settles on a single value. And because this limit never settles on a single value, that means it doesn't converge on a single value, so therefore this limit diverges. And because after the inconclusive nature of the alternating series test we got a divergent limit, that means that the original series diverges. Right? Now that doesn't necessarily mean this series goes to infinity, it just probably means that the series doesn't actually settle on a single value. Okay? So this series diverges. All right? So, hopefully these two examples made sense. We're going to go over some more examples in the next few videos, alright? So please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.